Welcome to the online course on pericyclic reactions and organic photochemistry. We are in module number 18 now. We will continue with sigmatropic rearrangement. There are certain topics still left in sigmatropic rearrangement, such as oxycope rearrangement, anionic oxycope rearrangement, and Claisen rearrangement, and so on. In this module, let us look at the oxycope and anionic oxycope rearrangement and Claisen rearrangement. Now, if you introduce an oxygen functionality in the 3 position of Cope system, what I mean is put a substituent with an oxygen which is a hydroxy or an alkoxy or a phenoxy kind of a substituent. This remote functionalization of this hexadiene unit accelerates the Cope rearrangement so much so that a factor of up to 10 to the power 15 enhancement in the rate has been observed for such system. So this is an oxycope system where the oxygen functionality is introduced in the 3rd position of the hexa 1,5-diene system. The rearrangement occurs considerably at a lower temperature, around 150 to 180 degrees centigrade, as against the 250 to 300 degrees Celsius for the normal Cope rearrangement. This can be realized by conversion of the oxygen functionality to the corresponding alkoxide in the terms of the anionic oxycope system. The anionic oxycope system is nothing but the anion of the hydroxy functional group generated by treatment of this alcohol with a base. As you can see here, the anionic oxycope systems can be synthesized by taking the allyl substituted ketone, in other words allylic ketone, and addition of a vinyl Grignard reagent will give you the tertiary alcohol. Such a tertiary alcohol is known as the oxycope system, and the anion generated by treatment of this tertiary alcohol in the presence of a base like tertiary butoxide constitutes the anionic oxycope system. It is in fact the anionic oxycope system which shows further rate enhancement of up to 10 to the power of 15 because of the remote functionality, which is the anion of the oxygen that is present in the system. So this is what I meant. The oxycope system undergoes rearrangement at around 150 degrees Celsius, whereas the anionic oxycope less than 100 degrees Celsius the rearrangement undergoes. You can see here the rearrangement essentially give an enol in this particular case. The enol undergoes the tautomerization to the ketone, so the final structure is essentially gamma delta, this is alpha, beta, gamma, delta, omega kind of an unsaturated system is what is obtained in the case. Whereas in the case of the anionic oxycope, the enolate is what is formed. It will stay in the enolate form until it is worked up to give the corresponding ketone. So acid treatment of the product of the anionic oxycope rearrangement essentially produces the ketone same as the oxycope system. Now this is an example of an anionic oxycope system where the tertiary alcohol, which is a vinyl substituted tertiary alcohol, is treated with potassium hydroxide and methanol. The anionic oxycope rearranged product is shown in this particular case. The bond that breaks is this particular bond. So starting from this sigma bond, if you count, it is carbon number 1, 2 and 3. On the other side it's carbon number 1, 2 and 3. So the 3,3 sigmatropic shift essentially would connect this particular carbon with the terminal carbon of the vinylic substituent, thereby constituting a 3,3 system in this particular case. Of course, this ketone will not stay like this in the presence of a base. This is a enolizable hydrogen, so it will undergo the enol formation followed by protonation to give a more conjugated system. This is a conjugated system, conjugated ketone, which is more stable than an unconjugated ketone of this type. So under the basic condition, the double bond isomerization will automatically take place under this condition. Initially, this rearrangement was thought to be a stepwise process involving the formation of an enolate and a vinyl ketone like this. For example, if you generate an oxyanion here, you can rearrange it to the corresponding enolate structure, which is this particular vinyl ketone structure. And the vinyl ketone structure and the enolate is intramolecularly can undergo Michael addition reaction to give the same product. But later on, detailed studies essentially showed that it is the concerted mechanism which is operative. The anionic oxycope rearrangement through this particular type of a transition state is what leads to the formation of this particular initial product, which undergoes double bond isomerization to give the final product. So although a stepwise mechanism is possible to explain the formation of the product, in fact experimentally it has been shown to be a non-stepwise concerted process of this kind going to the final product of anionic oxycope rearrangement in this system. Here is another example. The anionic oxycope system is prepared by the addition of vinyl magnesium bromide to this particular ketone. This is an allyl alpha vinyl substituted ketone. Addition of another vinyl group essentially constitutes the anionic oxycope system. Under the reaction condition, the 3,3 sigmatropic rearrangement essentially produces this medium-sized ketone. The medium-sized ketone, one of the prominent reactions that one can expect is the transannular reaction. This particular hydrogen in this position is acidic. So under the basic conditions of the reaction, the enolate of this particular alpha hydrogen is produced, and the enolate of course is in conjugation with this vinyl group, essentially producing the carbanionic center, vinylogous carbanionic center, which undergoes the intramolecular aldol type of a condensation to give this final product. So it is an anionic oxycope followed by a transannular intramolecular aldol cascade, which will explain the formation of this particular system. So essentially from a decolon system, we have synthesized a hexahydrophenanthrene kind of a system by means of this sequence of reaction that takes place in this reaction. Another interesting facet of the 3,3 sigmatropic rearrangement is the consecutive 3,3 sigmatropic rearrangement. In other words, a domino 3,3 sigmatropic rearrangement is what is taking place in this particular instance. This is an oxycope system. So under the basic condition, when treated with potassium hydroxide, the corresponding anion would be generated and the potassium salt would be generated. And the potassium salt is essentially the anionic oxycope system. So it can undergo 3,3 sigmatropic rearrangement to close this particular bond and open this bond by breaking of this carbon-carbon bond. So this is 1, 2, 3, 1, 2, 3. 3 bond is what is formed in this particular case. That in turn sets up another 3,3 sigmatropic rearrangement with the terminal vinyl groups. So finally the terminal vinyl groups undergoes the ring closure reaction to give this is the intermediate that is formed in the first 3,3 sigmatropic rearrangement, which is an anionic oxycope rearrangement, followed by the normal 3,3 sigmatropic rearrangement essentially produces this product. One can also visualize this to be formed by a 5,5 sigmatropic rearrangement, which is a competing reaction, could be a competing reaction in this particular system. This is a medium-sized macrocyclic ring system, and this macrocyclic ring system is essentially used for preparing the racemic mixture of muscone and the sembrane, which is a terpenoid molecule, for example. So these two molecules are essentially synthesized starting from this macrocyclic ring system that is synthesized by the consecutive or the domino 3,3 sigmatopic shift starting from this particular compound that is shown as the starting material. Here is an interesting example of a stereoselective Cope rearrangement. If you consider this molecule, this is nothing but an tertiary butyl dimethyl silyl, this is a thexyl dimethyl silyl oxy ketone. This is essentially a aldol condensation product. If you look at this is alpha beta hydroxy ketone is what is formed, beta hydroxy amide in this particular case. The X group is essentially this nitrogen substituted heterocycle. So this is an amide derivative and this is a beta hydroxy amide derivative. So essentially it is a aldol type of a condensation product. If you consider this is a syn aldol because the stereochemistry here is syn, whereas this is anti-aldol. Corresponding diastereoisomer is what is formed here, anti-aldol. Both of them undergo 3,3 sigmatropic rearrangement. In other words, the anionic 3,3 sigmatropic rearrangement, not anionic, oxycope 3,3 sigmatropic rearrangement. This is the vinyl group, one vinyl group. This is other vinyl group. So the 3,3 sigmatropic rearrangement essentially happens by the connectivity of the 3 and 3 position with the subsequent breakage of this carbon-carbon bond, which is the 1, 2, 3, 1, 2, 3. So this bond will be broken and this end of the terminal end of the vinyl groups will be attached to each other in a 3,3 fashion. In doing so, the reaction is highly stereoselective in the sense that the syn aldol product essentially gives the ZE isomer of the stereochemistry. This is the Z isomer and this is the E isomer of the stereochemistry of the olefins that is formed after the rearrangement takes place. The EZ isomer is a very minor product. On the other hand, if you take the anti-aldol condensation product, which is this particular product, the 3,3 sigmatropic rearrangement, which is the oxycope rearrangement, essentially produces the ZZ and isomer in the 60-40 ratio as it is shown here. So the stereochemistry of these double bonds are fairly well defined, which constitutes the stereoselective synthesis of this particular Cope rearrangement product that is formed. If you are wondering how the ZE is formed from the syn-aldol condensation product, one has to write the chair form of the syn-aldol. This is a syn-aldol where the two functional groups or the two hydrogens are syn with respect to each other. So this hydrogen and this hydrogen are syn with respect to each other. This is one particular conformation, chair conformation of this molecule. When the 3,3 sigmatropic rearrangement takes place, the carbon-carbon bond formation takes place between these two carbon centers, which produces, for example, the Z isomer of this olefin and the E isomer of the other olefin. So this alpha beta unsaturated ketone is the E isomer, whereas this enol ether is the Z isomer, which is formed as a result of the rearrangement, which can be explained by forming the 6-membered cyclic transition state in the chair form to give this. Now the thermal rearrangement of allyl vinyl ether to the corresponding gamma delta unsaturated carbonyl compound is known as Claisen rearrangement. This is the vinyl allyl ether. If you look at it carefully, this is a vinyl group and this is an allyl group connected to an ether, and this is a very first example done by Claisen himself on the rearrangement. If you look at this molecule carefully, this is nothing but the vinyl ether of the ethyl acetoacetate. If we consider this skeleton to be an ethyl acetoacetate skeleton, the enolic form of the ethyl acetoacetate has formed a ether with the allyl bromide or some such reagent. So allyl vinyl ether is essentially the enol form of the allyl ether of the enol form of the ethyl acetate is what is being considered. 3,3 sigmatropic rearrangement closes this bond, opens the carbon oxygen bond, resulting in the formation of the gamma delta unsaturated carbonyl functional group in this particular case. This reaction is nearly 100 years old now. This is a very first example that was done by Claisen himself. Apart from the Claisen rearrangement, there are many variations of the Claisen rearrangement are also known in the aliphatic Claisen rearrangement. These variations are very useful methods for the synthesis of the various carbonyl derivatives of the alpha beta unsaturated carbonyl compounds. It could be an ester, it could be an amide, it could be an acid, and so on. The reaction temperature for the Claisen rearrangement and its variation can typically range from 200 degrees Celsius for the Claisen rearrangement or the Carroll type of a rearrangement to temperature as low as -78 for the Ireland type of Claisen rearrangement. So the substituent in the X represented by X here can have such a large influence on the activation barrier, thereby lowering the temperature from all the way to the 200 degrees Celsius to nearly room temperature or even low temperature rearrangement can take place. Now the various variations that you see in the Claisen rearrangement or the Eisenhower Claisen rearrangement, where the substituent X on the vinylic position is a dimethyl amino derivative. In other words, it is a NO aminol of the ketene is what is generated here. On the other hand, if X group is a OR group, then it will be a Johnson orthoester Claisen condensation. If it is a trimethyl silyl or trialkyl silyl derivative, then it is an Ireland Claisen rearrangement. You can see here the Eisenhower rearrangement will give you an amide. The Johnson orthoester Claisen condensation will give an ester, which is a gamma delta unsaturated ester. The trimethyl silyl derivative will give the corresponding trimethyl silyl ester of the gamma delta unsaturated carbonyl compound by these three types of variations in the rearrangement process. Now if you look at the rearrangement of the allyl ester of ethyl acetoacetate, please recall here this is a allyl ether of ethyl acetoacetate, whereas in the case of Carroll Kimmel Cope type of rearrangement, this is an allyl ester of the ethyl acetoacetate. The enol form of the allyl ester of the ethyl acetoacetate under the reaction condition gives the product, which is this particular product. This is a ethyl acetoacetate molecule. The allyl, sorry, this is a carbon missing here. This should be allyl derivative. The allyl ethyl acetoacetate here is again one carbon is missing. The CH2 carbon should be there. This is an allyl ester of the ethyl acetoacetate in the enol form. The enol form, of course, will be in the hydrogen bonded nature in terms of the carbonyl hydrogen bonding to the enolic hydrogen. Under the reaction condition, it produces a carboxylic acid by a 3,3 sigmatropic rearrangement. The carboxylic acid is a beta keto acid, so it readily undergoes carbon dioxide elimination. Extrusion of carbon dioxide takes place to generate the gamma delta unsaturated ketone. This is called the Carroll Kimmel Cope type of rearrangement of the enol form of allyl ethyl acetoacetate. Now in the Asian-Mosher-Claisen rearrangement is essentially converting an alcohol to a amide of this type. Sorry, not the amide. This is the Claisen system, which is the Asian-Mosher-Claisen system, which is generated by treating this acetal, which is nothing but the acetal of N,N-dimethyl acetamide, by a trans-etherification reaction first. The trans-etherification reaction between allyl alcohol and this ketene, the N,N-dimethyl acetamide acetal, is essentially generates this molecule. Loss of methanol under acidic condition would generate the elimination of the methanol from this, forming a double bond here to generate this particular derivative. This derivative is what undergoes the Asian-Mosher-Claisen rearrangement to produce the gamma delta unsaturated amide, and this takes place typically around 150 degrees Celsius or so in terms of the temperature. The Johnson orthoester Claisen condensation, initially it is a trans-etherification reaction between the orthoacetate of this kind. The orthoacetate under the acidic conditions exchanges one of the alcohol, one of the methoxy group for the allyl alcohol to produce the corresponding allyl dimethyl orthoacetate, dimethoxy orthoacetate. Loss of methyl alcohol essentially generates the Claisen or the Cope, the Claisen condensation starting material. This is the orthoester Claisen condensation starting material, which undergoes the Claisen rearrangement to produce the gamma delta unsaturated ester. So the product of the Johnson orthoester Claisen condensation is essentially a gamma delta unsaturated ester is what is formed. If you look at this molecule, this is nothing but the acetate molecule. This is a allyl acetate. If you enolize the allyl acetate by treatment with lithium diisopropylamide and then quench it with trimethyl silyl chloride, you can generate the corresponding ketene silyl acetal of this kind. So this ketene silyl acetal is essentially an allyl vinyl ether which will undergo the Claisen rearrangement, which is known as the Ireland Claisen rearrangement, to produce the gamma delta unsaturated ester in the form of a TMS ester is what is formed. So these are the variations of the various Claisen rearrangement products that we have in the system. The mechanism of Claisen rearrangement is fairly simple. Claisen rearrangement is a concerted pericyclic process. However, there is an asynchronous process that is taking place in the sense that the carbon-oxygen bond breaking proceeds somewhat ahead of the carbon-carbon bond making. In other words, this is a simultaneous reaction but not a synchronous reaction. That's what it means. The extent of the CO bond breaking is much larger than the extent to which the CC bond is formed during the course of the rearrangement. The reaction proceeds through a chair-like transition state. We'll get to that in a minute. The chair type of a transition state is energetically slightly more favorable in terms of 2 to 3 kilocalories over the boat-like transition state. The negative entropy of activation essentially tells you that there is a high degree of order in the transition state during the course of this particular reaction. Now, if you consider the dimethyl substituted allyl vinyl ether, the stereochemistry of the product that is formed is going to be highly dependent on the stereochemistry of these two double bonds. Now, if you consider the various isomers that are possible here, the vinyl group, you can have the E isomer as well as the Z isomer. Similarly, for the allyl group also, you can have the Z isomer or the E isomer as in this represented in this particular case. So for this dimethyl substituted allyl vinyl ether, you can have 4 diastereoisomer EE, ZZ, ZE and EEZ, depending upon whether the vinyl group has the E isomer or the allyl group has the E isomer or the Z isomer, as the case may be. In each one of these rearrangement, the reaction is highly stereospecific in the sense the starting material geometry highly matters in terms of whether the erythro product is formed or the trio product is formed during the course of the migration. You can see here all the structures are already written in the chair form. The starting material chair form is written. If you form a carbon-carbon bond here, essentially one of the methyl group will be in this equatorial position, the other methyl group will be in the adjacent equatorial position, which corresponds to the erythro isomer. On the other hand, which corresponds to the trio isomer. On the other hand, if one of the methyl group is in the axial position, the other methyl group is in the equatorial position, that would constitute the erythro isomer. The two hydrogens are cis here. Here the two methyl groups are anti with respect to each other. You can see here diaxial 1,2 is anti. Diequatorial 1,2 is also anti, so this is a trio isomer. Here one of the methyl group is axial, the other methyl group is equatorial, so this is cis 1,2 axial equatorial is cis, so that's the erythro kind of a configuration is what you have. Now how do we write the chair form of the molecule is explained here. Let us take the example of the ZE isomer of the allyl vinyl ether with the dimethyl substitute allyl vinyl ether. What you do is first write a chair form of a cyclohexane nicely, and then substitute one of the carbon with oxygen, and then generate the vinyl group adjacent to it and an allyl group one carbon away from the oxygen atom. So this will be the allyl part of the ether, and this will be the vinyl part of the ether. So this bond has to be broken in the starting material, and this bond has to be broken during the course of the reaction. The CH2O bond has to be broken. So initially we get rid of this bond and then put the substituent such that one of the double bond, which is this double bond, the vinyl double bond is a Z isomer, and the allyl double bond is a E isomer. This is a vinyl double bond. So the methyl group and the carbon oxygen bond functionality should be cis with respect to each other. That is possible only when the methyl group is in the axial position and the hydrogen is in the equatorial position. In the chair type of a transition state, the substituents will occupy either the equatorial position or the axial position depending on the stereochemistry of the double bonds that are present here. You can see clearly here the hydrogen carbon hydrogen bond and the carbon oxygen bond are trans with respect to each other, constituting the Z isomer, because the methyl and the carbon oxygen bonds are cis with respect to each other, constituting the Z isomer. The other substituent, which is the allyl substituent, which is this particular substituent here, has to be trans because it's a E isomer. So unless you put this in the equatorial position and the hydrogen in the axial position, you cannot get the trans isomer. Now if you do the rearrangement by connecting these two bonds, you clearly see that the erythro isomer is formed, because these two hydrogens are syn with respect to each other, and that methyl groups are also syn with respect to each other. So this is a convenient way to learn to draw the chair form of cyclohexane and convert it in the either the Cope system or the Claisen system. If you introduce an oxygen in the ring, then it will be a Claisen system. If we don't introduce an oxygen in the ring, then it will be a Cope system, which was considered in the earlier module as we were discussing the Cope rearrangement at that time. Now a simple diastereoselective Claisen rearrangement is what is illustrated here. This is the EE isomer of the allyl vinyl ether. The EE isomer of the allyl vinyl ether undergoes the rearrangement to give only the trio isomer of the product. You can see here this methyl and this substituent are anti with respect to each other. So this is a trio isomer. Similarly, this is also the trio isomer. Under this condition, the erythro isomer is not at all formed, so indicating the high stereoselective nature of this particular Claisen rearrangement, which can be explained by a chair type of a transition state in this case also. Now here the Claisen system is synthesized by a trans etherification reaction. What we need is an allyl group is already there, so what you need is an vinyl group. So the vinyl ether synthesis is what is described in the first step. When you take ethyl vinyl ether and treat it with mercuric salt like mercury chloride or mercury sulfate in catalytic amount, the acidic nature of the mercuric sulfate essentially catalyzes the reaction, and instead of the ethyl group, now you have the allyl group that is attached to the vinyl derivative. So the ethyl vinyl ether is essentially a vinylating agent in terms of converting a simple alcohol into a vinyl ether derivative. Once you have the vinyl ether derivative, it undergoes the Claisen rearrangement to give the corresponding product. So you have started from the allyl alcohol, you have gone to the gamma delta unsaturated aldehyde in this particular case by a transformation, which is a Claisen first the trans etherification to get the vinyl ether, followed by the Claisen rearrangement to give the corresponding allyl vinyl ether in this particular case. Now several carbohydrate derivatives have been shown to undergo stereoselective Claisen rearrangement or the variations of the Claisen rearrangement. Here is an example of 4,6-O benzylidene D-allal, which is this particular skeleton in the pyranose ring form is written. This is D-allal. This derivative essentially is made to undergo several different types of the Claisen rearrangement. The first instance, this is an allyl alcohol which is converted into a vinyl ether by treatment with the ethyl vinyl ether and mercuric sulfate in this particular case, and heating the ethyl vinyl ether essentially sets up the stereoselective rearrangement. You can see here this is a 3,3 sigmatropic rearrangement proceeding in a suprafacial manner. So this stereochemistry is essentially retained in this product. So the final product is an gamma delta unsaturated aldehyde is what is formed in this particular case. In the second instance, Initially, an acetate is prepared of this allyl alcohol. The allyl acetate is enolized and it is quenched with tertiary butyl dimethyl silyl derivative in the form of the tertiary butyl dimethyl silyl derivative, which is a bulky protecting group, and this spontaneously undergoes, when treated with potassium fluoride, desilylation takes place and the enolate is generated. The enolate is an accelerated system for the Claisen rearrangement, which undergoes 3,3 sigmatropic rearrangement connected to this with this retention of stereochemistry at this place, same as the starting stereochemistry, resulting in the formation of a gamma delta unsaturated ester in this particular case in 61% yield. The same variation in terms of the Asian-Mosher variation is what is depicted. The D-allyl derivative is taken, it is converted into the ketene silyl acetamide kind of a ketene silyl acetal amide of the system is generated, which undergoes the Asian-Mosher Claisen rearrangement to give the gamma delta unsaturated carbon carboxamide is what is generated under this reaction condition. So the D-allyl derivative has been tested to undergo the simple Claisen rearrangement, the Ireland Claisen rearrangement, as well as the Asian-Mosher Claisen rearrangement to give the corresponding acid derivatives as the case may be. Here is a diacetate. This is a domino Ireland Claisen rearrangement of glycol acetate. This is a glycol acetate, this is a glycol, and the diacetate of the glycol is what is taken. When it is treated with the lithium diisopropylamide and a tertiary butyl dimethyl silyl chloride, the corresponding enol tertiary butyl dimethyl silyl ketene acetals are formed, and this is set up for a 3,3 Claisen rearrangement now. This is the bond that is going to break, and stereoselective syn suprafacial addition migration to this position essentially generates this particular system. This is now a vinyl allyl system again, so the domino process takes place. The first reaction takes place around 60 degrees or so, whereas the second domino reaction essentially takes place at a higher temperature, indicating that this is a much more facile rearrangement and the activation barrier for the second step is much higher. That is reflected in the relative K1 and K2. K1 is the first Ireland Claisen rearrangement, and the second Ireland Claisen rearrangement is the K2. The K1 by K2 is 35 in the case of this trans acetate derivative, 575 in the alpha methyl substituted derivative. It is 50 in the other derivative, which is a cis derivative here, 225, which is about the trans derivative with another acetate in this particular position. So the stereoselective nature of the retention of configuration at this position is what is illustrated in all of this allyl derivative in terms of the rearrangement, which is the domino rearrangement is that first rearrangement sets up the skeleton for the second rearrangement. That is why it is called a domino effect in terms of the domino Claisen rearrangement of the glycol acetates. The nitrogen analog of Claisen rearrangement is called asa Claisen rearrangement. Instead of an oxygen, which is the Claisen product, Claisen starting material, if we have a nitrogen, then it is an asa Claisen rearrangement. Here is an example of an asa Claisen rearrangement taking place of the vinyl allyl amine, which is a tertiary amine in this particular case, to get the corresponding imine. The imine is hydrolyzed in the presence of aqueous acid to generate the corresponding aldehyde. This particular case. This reaction can also be explained on the basis of a chair type of a cyclic transition state to yield this particular product starting from a particular stereochemistry of the starting material that is given here. So the chair type of a transition state is what is explained in these two pictures. For example, the R isomer of this particular derivative as an optically pure R isomer can exist in these two forms, and these two products that are formed are essentially explained on the basis of this. In this particular form, the methyl group is, the phenyl group is in the, this is the methyl group is in the equatorial position, which is a favorable situation. Here the methyl group is in the axial position, which is an unfavorable system. The rearrangement essentially produces these two types of products in this particular case. The thiaclaisen rearrangement is what is shown here. Instead of a nitrogen or oxygen, if you have a sulfur here, then the thiaclaisen rearrangement takes place. The corresponding sulfoxide reacts 45 times faster than the sulfide itself. So this is probably taking place at a low temperature. This is an vinyl allyl sulfide is what rearranges to give the corresponding thiaclaisen product. The thiaclaisen system is synthesized in this particular case by initially allylating this position. The S-allyl derivative is now set up for the enolate of the thiol Thiolate is what is generated by deprotonation of this position, and the corresponding thiolate is produced. Thiolate is alkylated because sulfur is a more nucleophilic center. S alkylation takes place using the allyl bromide in this particular case. So now we have set up a vinyl allyl derivative which undergoes a diastereoselective rearrangement through a cyclic chair type of a transition state to produce the 99:1 ratio of this particular diastereoisomer of the product. These are other examples of 3,3 sigmatropic rearrangement of an allyl thionochloroformate. For example, if we take this allyl alcohol and treat it with instead of a carbonyl chloride, the corresponding thiocarbonyl chloride, the corresponding thiochloroformate is what is generated. Thiochloroformate is a 3,3 sigmatropic system. It undergoes the 3,3 sigmatropic shift to give the corresponding product, which is this particular product. This is an acid chloride. The acid chloride is quenched with an amine to generate the corresponding thiocarbamate in this particular product. Now 3,3 sigmatropic rearrangement of propargyl acetate example is given here. The numbering as clearly tells you that this is a 3,3 sigmatropic rearrangement to give this particular product in about 50% yield. In this particular module, we have considered the oxycope rearrangement, the anionic oxycope rearrangement, followed by the variations of Claisen rearrangement. We have talked only about the aliphatic Claisen rearrangement. We still have not discussed the aromatic Claisen rearrangement, which we will discuss in the next module. This module, we have also shown the mechanism of the Claisen rearrangement to proceed through a cyclic chair type of a transition state, highly stereoselective nature of the cyclic transition state leading to a specific product formation depending on the stereochemistry of the double bonds that are originally present in the allyl vinyl ether has been illustrated with several examples. Thank you very much for your attention.